Algebra 1, this is lesson 2.9, day 3. So, today we're going to talk about uniform motion problems. A lot of this comes down to distance equals rate times time. So we should all know that. So, and there any modification of there, like time is distance divided by a rate, or a rate is a distance divided by time. So, what happens when we're talking about just one vehicle doing all the work? And this problem, the vehicle is skating. But it said it took Travis and Tony 40 minutes to skate 5 miles. The return trip took them 30 minutes. What was their average speed for the trip? Hint, I said find totals. So let's ignore that there's a hint there, and you guys are like, oh, average. So if I just find the rate of the guy the first time, the first trip, and find a rate of the second trip, can't I just average them together?
Maybe you can.
Well, could you do that with the mixture problems? You just add them up and divide by 2? No. Because remember, what we talked about with the mixtures is the one that you have more of tended to pull the percentage towards that more, right? So if you had more at 25% than, say, 40%, then you're going towards 25% instead of the 40%. So the same thing's going to happen here. So let's just look at some background information. Notice we have a time, we have a distance. We're talking about rates. So that means, shouldn't I be able to say that the rate R is equal to the distance divided by time? Would you guys be okay with that? Rate is equal to distance divided by time. And let's just assume the trip down, or the trip to the place, was R1. How far did they go on the first leg of their trip? 5 miles. How long did it take them? 40 minutes. Wait a minute, I think I could reduce that. 1 mile to 8 minutes. Oh, so they just went 1 mile in 8 minutes. That's not too bad, right? I mean, he's on skates, so I guess, he probably could have went faster. Well, how about rate 2? Rate 2, let's do our return trip. How far does he go on the return? Still 5 miles. He went back home. How long did it take him? 30 minutes. Which is 1 mile per 6 minutes. Definitely going faster on the way home, yeah? Because it took him less time. So his rate is bigger. Whoa, wait a minute. How does that work? If I divide it by 8 or divide it by 6, how come when I divide by 8 it actually is a smaller rate than when I divide by 6? Remember how fractions work? The smaller the number you're dividing by, the bigger the number that results. So 1/6 is bigger than 1/8. Because the numerator on top is based off of the same number, it's a 1. So 1/6 is actually faster than 1/8. Or, if I ask you this, the class won a jackpot. Does the class want 1/8 of it or 1/6 of it?
I want 1 whole of it.
1/6 would be a better option than 1/8, right?
Yeah.
Unless we're talking about green jelly beans.
What?
I don't know.
Green jelly beans.
I don't know.
That made
I guess no makes... Okay. Anyways, I tried.
Absolutely.
So, wait guys. According to this idea of average, would it be a good idea to take both of those, add them together, and then divide by 2?
Sure.
After what we just talked about? No. That would not be a good idea. But guess what? Let's do it anyways. 1/8 plus 1/6 divided by 2. The reason I'm doing this is because at the end we're going to find out what the real answer is, and we'll talk about the differences and why it's so. Would you guys agree that 1/8 plus 1/6 divided by 2 would be the average of those two rates? That is the average rate but it's not the average speed for the whole trip. So to get a common denominator, I think you'd have to put those together, yeah? So what's the common number between 2 and 8? And this is really over 1. I think you guys will hopefully agree with that. So what's the common denominator of an 8 and a 6? 24. So 3 and 3. And 4 and 4. Yeah? And so you end up with 3 plus 7 over 24 over, whoops, 2 over 1?
3 plus 4.
3 plus 4, which is, 4. Yeah, 3 plus 4. Not, ooh,
Uh-oh.
plus 4. Which equals 7/24 over 2 over 1. Now, what do you do when you divide by a fraction? Multiply by the reciprocal, which ends up being 7 over 48. That's interesting. So that means they can go, on average, they went 7 miles for 48 minutes. Is that what you kind of get out of that? See? 7 miles for 48 minutes. That's the wrong way to do that. Think of it this way, guys. You guys have taken long trips before. Say I'm going to Florida, because I am this summer, coming summer. Now, it should be about 22, 23 hours in a car. If I come back next year, you guys are like, hey, what was your average speed? I'm going to tell you it was 50 miles an hour, right?
Yeah.
That's not me going 50 miles an hour all the time, the whole time. Some parts of the trip I was going 70, 75. Other times I get stuck in Chicago's traffic and I'm only going 25, right? When I talk about the average speed of a trip, I'm taking all of the distances and all of the times, right? So, if I wanted the average speed, I sometimes now call it the, overall, overall average rate. That's why I come in saying it. Didn't look right. Overall average rate. Guys, overall average rate is total distance over total time. What this does, guys, it ignores the fact that there are individual distances and times or individual rates, and it says we got to lump it all together. So if my first trip on that car trip to Florida was 50 miles before I stopped, I'd have to take that one. The next one was 200, and then it was 300, and then add up all of those individual distances, and then add up all the individual times, divide them, and you have an answer. So, the OAR, average rate, for this particular problem, how far do they go, guys? First trip, 5 miles. Second trip, 5 miles, which makes a total of 10. But then I say, hey, how long did it take me to go? It was 40. How long on the way back? On that second trip for a total of 70. Wait a minute. That can be reduced. Which would be 1/7 or 1 mile per 7 minutes. That, guys, is the overall average rate. That was my average speed for the whole entire trip. 1 mile per 7 minutes. Now let's compare that to an answer that we found the wrong way. This rate here, guys, is directly in the middle between the two rates, right? I took a rate, added it to the other one, and divided by 2. I took the average of the rates. This one is the average speed of the whole trip. That means I added up all the distances divided by the total time. Now, this one has a 48 in the bottom. This one has a 7. I don't want to get a common denominator that way. What if we got a common numerator instead? If I made the top 7, I'd have to multiply by 7. But what I do to the top, I have to do to the bottom. We'll compare this. 7 out of 48 compared to 7 over 49. Of those two rates, guys, they're both miles per minute. So 7 miles per 48 minutes, 7 miles in 49 minutes. Which one's faster? The 48 one's faster. Why? Same reason we talked about the last time. It's a fixed number, 7 divided by 48, or 7 divided by 49. Hey, I got 7 pans of brownies divided by 48 people, or 49 people. Which group of people do you want to be in?
48.
The 48, why? It's bigger, right? You get a slightly larger piece. That's why. So this is larger. It's a larger rate. So that means this one's the smaller rate. But why is the smaller rate the overall average rate? Why does it seem to be on the say left side of the number line other than the average of the rates? Why is the overall average rate slower, right? Smaller, slower. Why is it a slower rate than the average of just the rates added together and divided by 2? Which trip took longer?
First one.
The first one. And in the first one, we went slower because we covered the same distance in more time. So, if we spent more time doing something slower, then your rate would have to be reflected to that, wouldn't it? Which means that's why it's slower than the average of the rates. Do you guys kind of see that? I'm using more of the 1/8 than I am of the 1/6. So that's why it's closer to 1/8 versus 1/6. Cool or not cool? Awesome. Green jelly beans, huh? Next one. Last one. What happens if we have two things going on? What if we have two people biking, two cyclists, begin heading in opposite directions on a circular bike trail that is 5 miles long? One cyclist travels at a 12-mile-per-hour pace, and the other one is busting it at 18 miles per hour. How long before they meet?
Let's find out.
Now let's think of this, guys. There's a 5-mile track, right? It's a circular track. They're going in opposite directions, so at some point on the other side of the circle, or the track, they'll meet. If the first guy goes 1 mile, how far is the other guy going to have to go?
1 mile. No.
4. If one guy goes 2.5, then the other guy will go 2.5. Now let's think of this. Will they meet directly on the opposite side, 2.5 miles each? No. The only way for that to happen is if they were going the exact same speed. So obviously one is going faster by quite a bit than the other. So the guy who's got the faster rate will go further. Now, here's a really cool thing. The distance between both of them added together is going to equal that 5 miles. Can you guys agree with that? So, would you also agree that each one has their own rate and time involved? That the rate of the first guy times his time added to the rate times time of the second guy will have the common difference or have a total distance that they travel together. Where R1, T1, R2, and T2 are the different bikers. Because what's rate times time? Distance. And so their distances together will make up the larger distance that they're going to cover. We know some of that. We know this. We know the distance is 5. What's the rate of the first biker? First guy's biking what? Yeah. Go ahead.
12 miles an hour.
12. We don't know his time yet, do we? What's the second guy? 18. We don't know this guy's time. Now we have an equation with two variables. Is there any connection between their times? Hey, they're even. Why? I don't want to say even. How about a better word? They're equal. Guys, T1 is equal to T2, but why? Not going to be multiples of 3. No, the times, not rates. Times. Two cyclists begin traveling in opposite directions on a circular track. How long before they meet? When they meet each other, are they going to keep going? Possibly not. Let's say the time stops there. Time starts when their back wheels don't touch anymore, right? Because they're right next to each other. So time starts and stops at the same time. So that's why time 1 is equal to time 2. So if that's the case, can I go back and fix time 2 to say it's, time 1? Or in this case, T1 and T2 is just time? I don't even care about T1 or T2. I could just call it time. And what's 12T1 plus 18T1? 12 plus 18. It's 30T1. Divide both sides by time 1, which equals time 2, will equal what? 5 over 30, or 1/6. 1 mile per hour. So it's going to take 1/6 of an hour. Oh, no. It's not miles, it's just 1/6 of an hour, right? Time. I did not use my unit analysis correctly, dimensional analysis. And if I don't like hours, I could change that to minutes. What is that in minutes? 1/6 of an hour is 10 minutes. So they will meet up in 10 minutes. Now, I could be that guy and not say, hey, when do they meet? I could ask you, how far does rider number 1 go? Then you just take your 1/6 hour, plug it into the equation. What's 12 times 1/6? What's 12 divided by 6? 2. What's rider 2? 18 times 1/6? 3. And 2 plus 3 is? 5. Okay, day 3, homework's on page 136, 11 through 15. Have a great day.